Hey there. Today we are going to look at finding congruent figures and congruent transformations. So two figures, points, line segments, polygons, etc., are congruent figures if and only if there is a rigid motion or composition of rigid motions. Remember, rigid motions are translations, rotations, and reflections like we've seen in the last few lessons that maps one of the figures onto the other. Congruent figures have the same size and shape. So as a visual, all of these shapes here are congruent because they have the same size and same shape, but the ones here are not congruent. They're all triangles, but they are all shaped differently. The side lengths are different, the angles are different. In a lot of what we're going to focus on today, we're going to be looking at figures in the coordinate plane and deciding if they are congruent or not. Some of these you can just kind of tell by looking at them, but we want to get in the idea of identifying the rigid motion or composition, which means multiple rigid motions that we use to get from one to the other. So how would I get from one starting pre-image onto an image that's the congruent or same figure? So the way we can do that is we can start with one figure, find the one that looks congruent to it, and see if I can do consistently the same action to get from the first one to the second one. So I'm going to start with the two squares here. They look congruent because they're both squares that have side lengths of 2 units. Let's think about the rigid motions we do to get from one square to the other. So I'm going to go from the bottom right corner A to the bottom right corner N. How do I get from A to N? It looks like I'm sliding or translating. I am translating 1, 2 to the left and 1, 2, 3, 4, 5, 6. And if I did that same motion to get, I could do that for all the other vertices. B would go to P, C would go to Q, D would go to R. So since I do the same transformation to get from every vertex, all the vertices of A, B, C, D to all the vertices of N, P, Q, R, those two figures are congruent. So square ABCD is congruent to square PQRN. And what we did was we translated 2 units left and 6 units down. Now let's check our other shapes. Are there any other shapes that look like they are congruent here? It looks like the two smaller triangles, HIJ and STU, are congruent to each other. They appear to be the same size, but let's think about what transformation we use to get from there, one to the other. If I rotate HIJ 180 degrees counterclockwise, I get to triangle STU. Our rule for that was, I'm going to pick the point H. A 180 degree counterclockwise rotation is X, Y, mapping to negative X, negative Y. So H, the coordinates of that point are 1, 2, 3, 4, 5. The coordinates of the point that would match up with that S are 4. I'm sorry, that should be a negative 4, 5. Negative 4, 5 for H. The coordinates of S are 4, negative 5. My handwriting today is awful. Let me fix that, please. 4, negative 5. So to get, I can see that I'm changing the signs of both coordinates there. So I'm going to say that triangle HIJ is congruent to triangle STU. And what we did was we rotated 180 degrees. The last two things that look like they are congruent appear to be the other two triangles, the ones we haven't talked about, EFG and KLM. And notice that they, one looks like an upside down version of the other, which means we probably have some sort of reflection going on here. If I reflect each of these points over the x-axis, I end up EFG maps to KLM. So I can say triangle EFG is congruent to triangle KLM. And what we did there was we reflected in the x-axis. You could also look at that with your coordinates rules. And if you reflect in the x-axis, that means xy goes to x negative y. If I take if I take E, that point is negative 1, 1. K, the point that would correspond with that is negative 1, negative 1. So we can see that's exactly what's happening there. So we had 3 sets of coordinate figures in this. Let's try another one. So same idea. We want to say which things look like they're congruent. So let's start with, let's go alphabetical. Does triangle ABC look like it's congruent to anything? It appears to be the same size as, it appears to be congruent to triangle DEF, but how? Here, it looks like it has turned or rotated 90 degrees. And so we can say triangle ABC is congruent to triangle DEF. Is rotated 90 degrees counterclockwise. If you want to check your rule for that, a 90-degree counterclockwise rotation is xy maps to negative yx. Pick a point. Let's pick A. A is at 5, 1. It matches up with D. D is at negative 1, 5. And we can see that's exactly what happened with those coordinates there. So ABC and DEF are congruent. Let's go with the next things alphabetically. We have a rectangle here and a rectangle here. How did I get from GHIJ to PQRN? Well, it looks like we just slid or translated down. Pick a point. I'm going to pick H. How do I get from H to P? I'm going down 1, 2, 3, 4, 5, 6. And if I do that same down 6 for all the other vertices, they match up as well. And so I can say that rectangle GHIJ is congruent to rectangle. It's not a very good rectangle, but you get the idea. PQRN. What we did there is we translated 6 units down. Last but not least, what have we not talked about? We haven't talked about those other 2 triangles. Are they congruent? Well, one is a mirror image of the other, which means there's some sort of reflection. If I reflect each point over the y-axis, then I end up mapping KLM to triangle STU. So I can say triangle KLM is congruent to triangle STU. How do we do that? We reflected in the y-axis. If you want to refresh on the rule for that, XY goes to negative XY. So pick a point. L is at negative 1, 1. T is at 1, 1. So our rule checks out. So again, we have 3 sets of congruent figures there. It is possible to have sets of figures that aren't congruent. If you see something where you don't have the same action happening for every single part of the shape, that means they're not congruent. Another name for rigid motion or combination of rigid motions is congruence transformations. So instead of saying find the rigid motion that gets us from one thing to the next, we can say find the congruence transformation that gets us to the one thing to the next. We call it a congruence transformation because your starting image, your starting picture, your pre-image, and your ending picture, your image, are congruent. So for this next one, they want us to describe a congruence transformation that maps parallelogram ABCD to parallelogram EFGH. So a lot of times you might have 2 motions that are happening to make things happen. First of all, notice that they're kind of pointing in different directions. This one is pointing up and to the right, whereas the image is pointing up and to the left. So it looks like we've had some sort of reflection going on. In order to make the blue parallelogram face the same direction as the green parallelogram, I need to reflect in the y-axis. So if I do that, A is 1 away from the y-axis. I go 1 away in the other direction, and I get A prime. B is 3 away from the y-axis. If I go 3 away in the other direction, I get B prime. C is 1, 2, 3, 4 away from the y-axis. If I go 4 away in the other direction, I get C prime. D is 2 away from the y-axis. If I go 2 away in the other direction, I get D prime. So if I connect those points, I end up with this orange parallelogram here. So first we reflect in the y-axis. Okay, we're closer. How do I get from the orange parallelogram to the green one? Well, it looks like it's just slid down. And so how many did I slide or move? Pick a point. Let's go with A prime. To get from A prime to E, I'm going down 1, 2, 3, 4. And if I go down 1, 2, 3, 4 for all the other points, I end up at the other vertices. And so then from there, we translate 4 units down. And so the combination of both the orange and purple reflecting in the y-axis and then translating 4 units down is the congruence transformation that gets us from the starting blue parallelogram to the ending green parallelogram. Let's try another one. So this time we have triangles, but it's the same idea. Notice they are facing in opposite directions, sort of a mirror image, but then there's another thing going on as well. We're starting with the blue one. If I want to get it basically upside down like the green one, I need to reflect it in the y or x-axis. So let's do that first. I'm going to start with K. K is 1, 2, 3, 4 away from the x-axis. I go 4 away in the other direction, and that gives me K prime. L is 2 away from the x-axis. 2 away in the other direction gives me L prime. J is 2 away from the x-axis. 2 away in the other direction gives me J prime. So this purple is kind of my in-between triangle. How did I get the in-between triangle? I reflected in the x-axis. Now, how do I get from the purple triangle to the green triangle? It looks like it just slid or translated. How far did we slide or translate? I'm going to go with this bottom vertice, K to N, and see how it moves. I'm moving 1, 2, 3, 4, 5. So, and if I check it out, 1, 2, 3, 4, 5, I end up at M. 1, 2, 3, 4, 5, I end up at P. They all are the same. So then we translate 5 units to the right. So the combination of the purple and the orange is my congruence transformation. To get from JKL to MNP, I first reflect in the x-axis, then I translate 5 units to the right. In the next video, we will talk about checking things in Desmos to find whether polygons are congruent.